We're going to go ahead and look at standing waves now. So when you have a wave like on a string and you jiggle a jump rope up and down or something, it'll bounce back. And if you keep jiggling that jumping rope, it'll keep interfering with itself. Now, when it jiggles and makes it bigger, that's an antinode. That's right here. That's this part that is bigger or taller and it goes up and down, up and down. And then the node is right here. That's the spot where it doesn't move up and down or all. And that's because one of the waves might be going up and the other one's going down, and they both meet at the same place at the same time and cancel each other out. And so you'll have a node there. So I want to look at some examples of this. So what you just saw was this thing going up and down, up and down. And right here and right here, it did not go up and down at all. So these are your nodes. And the rest of this kept going up and down, and that would be your antinode. And when it was going up and down, you probably noticed it also looked like it went down here like this. So that's where it's going up and down really fast. But these nodes are where it doesn't go up and down at all. And so this, I need to figure out how much of a wave this is. Well, if I start here and I draw one wavelength, it'll look something like this, which means that when I get to this point here, that is half of a wave. So from here to there is half of a wavelength. That's a symbol for wavelength. And whatever this distance is, I'm going to call that L. So that's the length or distance of my string. Usually it's not nearly this up and down. It's fairly flat like a guitar string or a piano string. So the length of the string is going to be basically straight and the same. But to show you in the video, I wanted to do it like this. So if I wanted to find my fundamental frequency, I need to figure out what that is. Well, I know that velocity is equal to frequency times wavelength, but I don't know my wavelength. Instead, I know this relationship that 1/2 of the wavelength is equal to that distance. So if I multiply both sides by 2, I will get that my wavelength is equal to 2L. And then I can plug that in here into the velocity is equal to frequency times wavelength. Now, if we're talking about sound, that velocity is going to be 343 for sound. But if it's not sound, then it's going to be equal to, and I'll write it over here, velocity is equal to the square root of that force or tension divided by the mass per unit length. And so that velocity we can figure out if we know about the string on a guitar or piano. Otherwise, it's 343 if it's sound. And then once I have that, I can solve for it. And so for right now, I'm just going to solve for frequency. So I'm going to divide both sides by my wavelength. And then I'm going to substitute in here. So my velocity divided by my wavelength is equal to my frequency. But I don't know my wavelength, but I figured out a relationship for it. So I'm going to stick that in here. So my velocity divided by 2 times the wave, or 2 times the distance or length, is going to be my frequency. Okay, that's really cool. But that's only for my fundamental frequency. What about if it was wiggling faster like this? So in this case, you had a node here, a node here, and a node there. And it's exactly one wavelength. So in this case, my wavelength is going to be the same as the length of the string. And then if I wanted to do velocity is equal to frequency times wavelength, plug in my relationship here, then I'm like, oh, look, velocity is equal to frequency times L. Divide both sides by that frequency. Oops, by that length, I mean. and I get velocity over the length is equal to my frequency. All right, well, that's cool. And what about if it's like this now? Let's watch that video.
Notice the nodes are not moving at all, and that at both ends there is a node.
All right, so now I have 4 nodes here. And if I look at that, I can see there's one wavelength here plus a half of a wavelength. So that means whatever the length of my string is 1.5 wavelengths. Now I will warn you, I would do this in fractions, like say length is equal to 3/2 of a wavelength. Because what we're going to do next is we need to solve for that wavelength. So the easiest thing to do is leave it in fraction form, because then I can go times 2 divided by 3 on both sides. And then I have 2 divided by 3 times L is equal to my wavelength. So I can figure out my wavelength then if I know the distance L, and I know that there's 3/2 of a wave here. And if I'm looking for the frequency of this wave, again, I could do velocity is frequency times wavelength, plug in wavelength there, and then solve for it. So velocity divided by my wavelength is my frequency. So velocity divided by 2/3 L is our frequency. All right, so you should notice that there's this, like, he keeps adding 1/2, keeps adding 1/2. And so that is true. I feel like it's easier for me to think about these and draw them out than it is for me to actually use the equations that they give you in the book. But if you love equations, the equations for the standing wave in a string, and you'll notice that every single one of these just goes up by a half wavelength, because you're just adding an extra half of a wavelength every time. So let's say you have a marimba. Now, a marimba is basically a whole bunch of different lengths of tubes that are open at both ends. Well, sound is different in the way that it resonates in a tube like this, in that you need an antinode at both ends of an open tube. So when you have an open pipe, the smallest length of pipe that you can hear a sound is when you have this, and this is actually going to be half of a wavelength as well, because you're going from down here up, and then to go back down again would be another half wavelength. So the length of this pipe is equal to 1/2 wavelength. You can solve for that, and then you can figure out whatever you need from there. The next time is going to be when you have an antinode at both ends. So here, I'm going to go from the top to the bottom to the top again, so that's 1 full wavelength. And then here, we're going to go from the top, bottom, top, so that's 1 wavelength, back to the bottom, that's 1.5. So this will be exactly the same equations for the string that was fixed on both ends. But some pipes are closed on one end. For example, a flute or clarinet, where you're blowing on one end and the other end is open, or trombone or trumpet or something like that. And that's what I want to show you next, is I am able to use a tuning fork and a thing of water to find these lengths. So here I have on the left, these guys are open and closed, just like what you saw, where this end is closed and this end is open. This is one where it's open on both ends, like the marimba I showed you. And then this is like over here, these are like your guitar and piano strings. And so you can see how this is a quarter of a wavelength, because I need to go from a node at the end where it's closed to an antinode at the other end. And if I were to keep drawing this wave, I need to go from node and not just back to node again, but I need to go all the way back down and back up to get a full wave here. So this is only 1/4 of a wavelength.
Alrighty, so we're going to look at constructive interference, specifically for a pipe that is closed at one end and open on the other. And so this pipe currently has an open end at both sides. And the problem with this is that you would have to get exactly the right pipe for this to get louder. But what I'm going to do is I'm going to put it in water. And when I put it in water, I'm essentially both closing this one end of the pipe and I'm able to stick it farther and farther into the water so that I can change the length of the pipe, so I can find exactly when I get constructive interference. And it's going to sound louder when I have constructive interference, and it'll sound quieter when I have perfectly destructive interference. The destructive is really hard to hear because you're going to have the tuning fork making sound that's coming out and not necessarily getting destructively interfered inside the pipe, but it's going to be really obvious when it's constructive. And I'm going to hold at that point, and then I can measure how far it is sticking out of the water. So you measure it from the top of the water to the top of the pipe, because that's how long the pipe is. So this one right now is 14 centimeters. And this tuning fork is 512 hertz. So that's going to be the first time that it makes sound. And then I can look for the next time. Which is about right there. And you'll notice I'm holding the meter stick in a different place because the water level changed as there's less pipe in the thing. And now we're at 48.5.
To equal the length of this pipe. And so if that's 1/4 of a wavelength, then I can figure out the actual wavelength of this pipe. So if I measured it like I just did, and I found, for example, that I got 14 centimeters as my length for that first one. So that's 0.14. And I want to know the wavelength of my pipe. So the wavelength is 0.52 meters. And then I did it again, but this time I had a longer pipe. And so this time I went until I got the next one. So I had its node, and then here's my first antinode. So this is where I could end, but I didn't because I wanted to find the next one. Okay, so here I'm back to a node again. Got to make this pipe longer. And then here's my next antinode is right there. All right, so at that point, I'm going to look at where a full wave would be. So I'm going to stop here. But a full wave, I would go up, down, and back up to the same starting point again. So I'm at 3/4 of a wavelength. So 3/4 of a wavelength is equal to that length L. And when I did this, I got 48 1/4 for my length when I measured that, so 48.25. And I then was able to solve for my wavelength. So my wavelength then is 4/3 times the 48.25. And so that gives me a wavelength of 0.64 meters, which is actually pretty close. And in fact, what actually is happening with these tubes is the end of this, where the antinode is actually happening, is a little bit beyond the end of this. So if I'd gone a little bit farther out, I would have uh, been able to get exactly the same with this if these were just, if I added a little bit more here outside of the tube. And you can actually calculate that and figure it out to get the exact wavelength, because if I subtract these two lengths from each other, it'll be exactly half of a wavelength, because whatever this is on the end, this part here is the same as this part here. And so what's left is this half of a wavelength. And so if I'm like, oh, I see these two lengths and I can subtract them from each other. So if I subtract those two lengths of the pipe from one another, I know that half of a wavelength will be equal to 0.3425. So then my wavelength itself is going to be 0.685. So pretty close. And you can see the approximation is pretty good there. And then if you want to look at what each of these things are called, your first harmonic, or the fundamental frequency, is going to be that one that is however the smallest thing is that you can get it to constructively interfere or to make it louder or what have you. That's this one. Your second harmonic, you don't have one for a closed open pipe. The third harmonic you do, the fourth you don't. So this is kind of interesting to look at it and see how each of these things are called. And then if you're in music, you actually know what these are and you can hear them. So the last thing to remember, of course, is that these equations from before are still the same. Like if you're trying to find the velocity of a wave on a string, it's the square root of the tension over m over L. And if you are looking for the velocity of sound, it's still 343. Of course, unless they tell you that you're on a different planet or there's something weird going on or it's extremely, extremely cold, just use 343 for that speed of sound in air. And then you'll be able to find frequencies and wavelengths, and you can cross-check it with your tuning forks and all that good stuff. Let me know if you've got questions.
All right, so now we're going to go ahead and do some calculations on that. But first, before we do that, I want to now go ahead and switch to a different diameter pipe. So this is a skinnier pipe, this is a thicker pipe. And I want to look at how that affects it. So I know that I should have it at about 14 or 15 centimeters. So this is not short enough for me to get that first one, but I should still see one at 48 and a half or so. Right there. 48. So the diameter of the pipe doesn't matter. The only thing that matters is the length of the pipe. And then the other thing that matters is the frequency of the tuning fork, because the frequency is going to be directly correlated with the wavelength. And so as the frequency increases, my wavelength is going to decrease. The velocity of the wave is going to stay the same because it's going to be just the velocity of sound in air. So this tuning fork is 488. 27. Okay, so not long enough. I need to go longer. It's about right there. Which is at about 86 and a half. All right, so looking at this is about 15. If I triple it, I get about 45, so that's right on. And then this, if I go 27 and I triple that, I get about 80. So we're right there looking at half of a wavelength and 1.5 wavelengths.